Hello everyone, welcome to lecture 29 of the online course on modern display technologies, flat panel display. Today's lecture will be on LCD matrices and driving scheme. So this is the first part of the lecture. We'll have more discussion on the next one as well. Here's the lecture outline. We'll have a brief introduction to the topic. We'll talk about the segmented displays, then the XY matrix, and then we'll find out the scheme for addressing an N cross M matrix and how to set up a simple drive scheme. So let us start with a big picture. So LCDs are everywhere, from simple wristwatch displays to large screen televisions, precisely because they are flat, lightweight, energy efficient, and they operate at low voltage compared to the older technologies like CRT. Some other recent applications also include like head mounted displays, direct and projection TV, direct view and projection TV, the e-paper and the e-books as well. Okay. Now, as I mentioned, the key advantages are form factor, the low weight, energy saving operation, and also the low drive voltage. Now just a quick reminder about the physical mechanism of LCDs. So LCDs basically do not emit light themselves. They basically modulate the intensity of the light passing through via their birefringence, and you can apply an electric field to reorient the liquid crystal's director because of this dielectric anisotropy, or in ferroelectric materials. So that is the mechanism through which now you can get the bright or the dark state. So in short, you can say that the liquid crystal directors can be reoriented by applied electric field based on the features like dielectric anisotropy or ferroelectricity. Okay, and this makes it possible to generate spatially patterned images. So now the today's question is that given a single liquid crystal cell can show one uniform state, how do we build a multi-pixel display and how we control independently every pixel? So that is where we'll see these particular methods or methodology in this lecture. Okay, so this slide basically introduces the simplest possible multi-pixel LCD architecture, that is the segmented display. So in a segmented display, every display element, that means every segment, has its own dedicated electrode. Okay, so here is a picture of 7 segment numerical display. Okay, so the schematic diagram of this segmented numerical liquid crystal display is shown here. So voltage can be applied to each segment independently. So these are also called the direct drive displays, right? Now if you look into this particular figure, this is a 7 segment numerical display with only one common cathode, and you have got 7 segment electrodes. Now to display the numerical 5, okay, what you will do, you apply the switching voltage between the common electrode and the segments 1, 2, 4, 6 and 7, right, like this. So that way those regions will turn on and the others will stay off, and your eye can basically read the pattern 5. Now what are the limitation? The limitation here is that since every element needs its own electrode and its own driving line, so this approach only scales to displays with small number of elements such as calculators or simple numeric or icon displays. Okay, not anything with many pixels such as TVs or a phone screen. Okay, so here we will introduce the key structural idea that makes high resolution LCDs practical, that is the XY matrix. So here what is the main fundamental? So instead of having one electrode per pixel, you can basically use two sets of parallel stripe electrodes. Okay, so one set is for columns on the front substrate and one set for the rows on the rear substrate, which are oriented perpendicular to each other. Okay, so this is the schematic diagram that clearly tells you this. Okay, so what is the key idea? So whenever a front stripe crosses a rear stripe, that overlap region is one addressable display element, which is called the pixel. So you need to select the front and the rear electrodes, and the intersection point basically will get activated. Okay, so only where the liquid crystal is sandwiched between an energized front and rear electrode, okay, there an effective field will appear. Okay, so you can basically see that here in the case of having, say, n rows and m columns, so altogether you can have n cross m number of pixels, but you don't require that many number of electrodes, you just require n plus m electrodes. Okay, not n cross n. Okay, so that is where you basically save a lot of number of electrodes, and that gives you a practical solution. Okay, so for any n row by m column display, you are now basically getting only n plus m electrodes to address n times m number of pixels. So that is like a huge simplification for something like a million pixel display. Okay, because anything like n cross m number of electrodes would have been impossible to wear, but this is much simpler. However, there is a catch, because now the pixels basically share electrodes with their neighbors. You cannot simply turn on one electrode pair without some voltage inevitably appearing across the other pixels too. That means driving the matrix correctly becomes a real engineering problem, which is what we will be discussing in the next section, right? So that means there will be crosstalk. Okay, so here we are basically addressing a problem which is concrete with the smallest possible example. So we are considering a 2 cross 2 matrix. So let us consider this simplest possible case of 2 cross 2 matrix, where you have these 2 rows and 2 columns. Okay, and the liquid crystal pixels are basically modeled as capacitors in this equivalent circuit. Okay, so these are your voltage lines. Okay, and these are the row lines. Okay, or you can say these are the 2 row electrodes, these are the 2 column electrodes, and these are the intersection points. Okay, so you can name the pixels also. It is pixel 1 1, that means row 1 column 1, 1 2, so row 1 column 2, pixel 2 1 and 2 2, and so on. So say the goal is to only switch on the pixel 1 1. Okay, so what you will do, you will basically you will apply voltage V to this column 1. Okay, and you want the row 1 to be 0, so that this voltage drop appears across this particular pixel. So what is happening, you are basically giving, or you are applying a voltage V across this pixel P11. Now what is the problem here is that due to the capacitor network, you will see a voltage of V by 3 will also appear across the other 3 pixels. Okay, that is in 1 2, 2 1 and 2 2, they will have this V by 3 voltages, which are all in parallel. Okay, so they are basically getting some sort of voltage. So only our pixel 1 1, which is sitting at the intersection of this row 1 and column 1, it basically sees the full voltage V applied across it. Okay. Now this problem is coming because the pixel capacitors are all interconnected through this shared row and column lines. Okay, so that is why a voltage of V over 3, okay, also appears across the other 3 pixels in the simple network, even though we do not intend to address any of them. Okay, so what is happening, this unwanted voltage appearing on these pixels, okay, this is only known as the crosstalk. Okay, and this is the central obstacle to every passive matrix driving scheme, okay, including the one developed in the rest of this section, okay, where we'll show that you can specifically design this kind of driving scheme to minimize this crosstalk. Okay, so a real display is basically addressed one row at a time, so it is called a line at a time scanning. Okay, so you are not scanning all the rows at once. So the row electrodes can be also called as the scanning electrodes, and the column electrodes can be named as the signal or the data electrodes. So the optical state that you see of every pixel is basically getting controlled by the voltage pattern that you are applying to this signal electrode, which is the column electrode. Okay, while that particular row of the pixel, okay, is being scanned. Now because each row is only actively driven for a brief instance per frame, okay, the liquid crystal pixel basically behaves like a capacitor that partially retains charge, and the design of the row column voltage waveform, okay, becomes critical to getting the right pixel states, okay, while minimizing the crosstalk. So in short, you can understand that each row is only actively addressed for this small fraction of this total frame time, yet we need each pixel to be stable. Okay, so the correct optical state should be shown for the entire frame. So this tension combined with the crosstalk coming from the other rows and column voltages, okay, this is the thing that you will be addressing in the next slides. Okay, so here are the 3 key issues that you see in this kind of matrix addressing. So the first one is that the column voltage basically create unwanted voltages on pixels, okay, particularly in the not being addressed rows. Okay, so this is called crosstalk, which you have just seen. The second issue is that the voltage across a pixel is not retained or held once its row has been finished being addressed. Okay, so after the scanning gets over, that voltage is not held, and the time frame, that is the time to scan all the n rows once, will be simply Tf, that is n into delta t. So say there are n rows and each row requires delta t time, so that delta t is basically nothing but the time to address one row. Okay, so now Tf is the overall frame time. So the constant comes to us is that the Tf must be shorter than both the human eyes response time, that means below 40 millisecond, and the liquid crystal's own relaxation time, so that our eyes do not basically see the change in the pixel intensities. Okay, now if the, or you can say when the Tf is shorter than the liquid crystal relaxation time, the liquid crystal state in that pixel is set by the RMS voltage which is applied across it. You can average it over the whole frame time, and the key physical fact behind everything, this is the key physical fact that basically is responsible for everything that happens after that. Okay, so in short, if I want to explain this again, that why this second speed constraint matters so much. Okay, so you can understand this by thinking that when the frame time is shorter than the liquid crystal's relaxation time, the liquid crystal cannot track the first changing instantaneous pixel voltage, and instead it basically responds to the RMS voltage averaged over the whole frame. And this is the main physical fact that the entire RMS voltage drive scheme derivation, okay, depends on. So we'll discuss this in the next slide. So why this RMS voltage? So this particular slide will explain that the single most important physical principle behind passive matrix LCD driving scheme is the RMS voltage averaging. Now, because the frame time is deliberately kept shorter than the liquid crystal's own relaxation time, the liquid crystal director physically cannot respond to, that means it cannot track the first jagged instantaneous voltage waveform that a pixel actually experiences within a particular frame. Instead, the liquid crystal basically responds to the root mean square voltage, which is basically the averaged voltage over the full time frame TF. Okay, and as I mentioned, this is the physical basis of every passive matrix drive scheme. Even though a pixel's instantaneous voltage jumps between several different values within one frame. Okay, so when I say within one frame, it is basically its own addressing slot plus n-1 crosstalk slots when that pixel is not basically addressed, but still it will have some values, right? So what will matter for switching is basically its RMS average. Now, how do you set up a simple drive scheme? Okay, so here we'll discuss about setting up this specific drive scheme problem, and here we will solve algebraically a simple standard scheme following the Alt and Plashow's classic analysis. So let us first consider a normally black LCD. So here at V equals 0, the transmittance is 0, that means you are seeing a black or dark state, and at V equals V on, the display basically switches to a bright state. Now, as a selected pixel is one we want to drive into the bright state, and a non-selected pixel is the one that we want to keep in the dark state. Okay, so what is the goal for the drive scheme? So our goal is that make the RMS voltage on selected pixels as different as possible from the RMS voltage of the non-selected pixel. That means you are basically maximizing the contrast while minimizing the crosstalk. So here we will lay out the specific voltage scheme whose consequences we will derive algebraically. So the first thing is that the column voltage required to select the bright state can be minus V by B, and the column voltage required to select the black state is plus V by B. Okay, so these are just two column voltage levels. The negative V by B is used to select the bright state of the pixel for the currently addressed row, and the positive V by B is basically used to select the black state or the dark state. Now there are two row voltages level. Okay, the row actually being addressed will get B minus 1 V over B. Okay, whereas the other rows they will get exactly 0. Okay, now what is this B? B is a free design constant. Okay, so you do not need to fix it immediately to any number. Its value can be chosen later on depending on the number of rows you are going to select and all. So right now you can think of B as a knob that you can use to optimize. So for the selected pixel, while its row is being addressed, the applied voltage is basically the row voltage minus the column voltage for the bright state. That means you have B minus 1 times V over B minus the column voltage, that is the minus V by V. So this basically gives you V. Okay, this is the applied voltage V, which is nothing but the row voltage minus the column voltage, right? So if you simplify this, you will get something like this. Okay, so what it tells is that during its own row's addressing slot, the applied voltage is the row voltage, that is B minus 1 V over B minus the column voltage for the bright state, which is minus V over B. Okay, so when you are basically subtracting a negative quantity, that is basically adding it up. So when this thing adds up, okay, you are basically getting exactly V, right? Now this confirms our scheme that you are correctly delivering the full switching voltage V to the pixel for which the row is basically getting selected. Now during every other row's addressing slot, there are basically n minus 1 of those per frame. Okay, so what you do there, the pixel's own row voltages is 0, okay, for those non-addressing ones. So the voltage it is going to experience is nothing but the column voltages, okay, coming from the actually selected pixel. So this, the voltage will be 0 minus whatever the dark or the bright state that you are getting. So it can be plus minus, so you can get it is as V by B. Okay, so during the other n minus 1 row addressing slots in the frame, so the final crosstalk is basically coming from the column voltages which are remaining, that is V by B. So you can understand that if you want to reduce the crosstalk, you can basically increase B. Now for the non-selected pixel, while its row is being addressed, the applied voltage is basically the row voltage minus the column voltage for the black state. So you can write this as, this is the applied voltage to the row minus the column voltage for the dark state, which is V by B. Okay, so this basically gives you B minus 2 V by P, and this is for the, so this the top one is basically for its own rows addressing slot. So you are getting B minus 2 V by B, and for the other n minus 1 slot, this is the one you are getting, that is only V by B, because the row voltage for the non-addressing slots are 0. Okay, so you are basically getting the identical crosstalk contribution to the selected pixels case, like this one we have discussed. So this is the non-selected one. In the previous slide we have seen the selected pixels case. In both cases the crosstalk is same, V by B. So now let us look at the RMS voltage on the selected pixel. So averaging the squared voltage over all n row addressing slots in one frame. So you are basically having one slot at V, perfectly applied V, and in other n minus 1 slot the voltage is basically V by B. So you can take the square root, okay, that will basically give you the RMS voltage for the selected pixel. So the RMS value can be root mean square value can be square root of, so V square plus n minus 1 times V by B whole square. The whole thing you are dividing by the total number of rows, that is n, and you are taking, so this is the root of the mean of the square of the voltages. So this is the how RMS is basically calculated, and this is the effective voltage that the liquid crystal actually sees and responds to. Since your frame time is shorter than the liquid crystal's relaxation time. Okay. Now what about the RMS voltage on the non-selected pixels? So you can use the same averaging process, but in this case for the non-selected pixels, the voltage in the one slot is only B minus 2 V by B, it is not V. Okay, you are getting this voltage in the non-selected pixel, and the remaining n minus 1 slots you are getting V over B. Okay, so I am using this V by B or V over V interchangeably. Okay, so you may call it in only one fashion to avoid any confusion. So here the RMS calculation for the non-selected pixel will look like this. So this is called VNS, that is non-selected. The previous case was VS, that is the selected one. So you are doing square root of this voltage B minus 2 into V by B whole square plus n minus 1 times V by B whole square, and then you are dividing the whole thing by n and taking a square root. So what you see is that to get a good contrast, you want this VNS to be as small as possible as compared to VS, and this will basically give you the contrast ratio. This can be quantified next by a ratio R, that we will see later on. So with that we conclude this lecture. If you have got any query on this, you can drop an email to this to my email address deb.sikdar@iitg.ac.in, mentioning the course name and the lecture number on the subject line. Thank you.